Now let's consider the first law of thermodynamics. As we said, Q minus R equal to delta U. And this term delta U is equal to mass for a closed system multiplied by specific internal energy U2 minus a specific internal energy U1. This term actually, in case if the working fluid is steam or refrigerant 134A, so in this case I will be using tables, and I think you have learned how to use a steam table in chapter 3. So I may actually make another video to show you how to use a steam table or refrigeration table. But anyway, in this case we need to calculate U1 minus U2 for steam or something or refrigerant undergo change from initial state 1 to a final state. So in this case at point 1, in this case we can just go to the table and then we can get the value U1. And also at point 2, let's say pressure and temperature are given, then you can go to the table and calculate U2. Either this table is steam or refrigerant. You have to decide about the working fluid. If it is steam, so in this case we can use tables from table A4 up to table A7, and if it is refrigerant 134A, you can also be using tables from A11 up to table A13. So in this case, the condition at point 1 will be given to you. Let's say pressure and temperature B1, T1, and here B2, T2. Just you can go to the tables and you can get U1 and U2. So in this case, if the working fluid is steam. Now the second case, if this working fluid is liquid or solid. So in this case, or incompressible substance in general. So in this case, we can say delta U will equal to C average. In this case, we don't have CB or CV, it's a solid or liquid, so we don't have CB or CV, just it's C average multiplied by T2 minus T1. And this C average is calculated from table A3 depending on the substance. So if the substance is, we do have a closed system, if it is liquid or solid, so in this case delta U will equal to C average T2 minus T1, and C average is just calculated from table A3. The third special case, when we do have the working fluid is gas, and in this case we do have 3 cases. Let's consider the first case, 3A. If he asks you actually to consider the constant specific heat analysis, so in this case we can just substitute delta U. We do have the definition, by definition delta U integration of CV as function of temperature dt from T1 up to T2. If the temperature difference delta T is small, we can just take this C average, consider it as a constant or it's changing linearly, so we can consider it C average, take it outside. So delta U will equal to CV average multiplied by integration of delta T, which will equal to T2 minus T1. And this C average is calculated as the average temperature T1 plus T2 over 2, and then you can go to just table A to B, then we can get the value of CV average. Okay. Get CV average, then we can just substitute C average delta T, then we can calculate delta U. Okay. But this is the first special case when we are following constant specific heat analysis. The second case, when he asks you to follow the variable specific heat analysis. So in this case, just to say delta U, like steam or refrigerant, will equal to U2 minus U1. And in this case, but the working fluid is gas in this case, I will be using one of the tables from table A17 up to table A25 depending on the substance. For air as example, this is table A17. Then at this case, at temperature T1, you can just go to the table get U1, and at temperature T2, you can just go to the table get U2, and you will say delta U equal to U2 minus U1. depending on the given substance. And this is actually the second case. There is a third case which is using the integration to calculate delta U. So in this case, we have to do the integration, get CV as function of temperature, and in this case, just substitute in this equation delta U equal to CV integration dt, and then we can get the value of delta U. But actually this case may not come to your exam because it's a time consuming case. So he will be asking you either to follow constant specific heat analysis or variable specific heat analysis. But let's say just write down, just maybe for your knowledge, 3C. In this case CV will equal to, delta U integration of CV as function of temperature dt from T1 up to T2. In table A to C, you will find in this table is giving an equation Cv bar, which is in kilojoule per kilomole Kelvin, is function of A plus Pt plus Ct square plus dTq. All of this constant A, B, C, D are depending on the substance, so it will be given here the substance, and those constant A, B, C, and D are given depending on the substance. So just we can take it and substitute here, but we will get CV. I need CV, so CV per mole also will equal to CV per mole minus R bar, which is the universal gas constant, 8.314 kilojoule per kilomole Kelvin. And if you don't remember this value, just you can get it from table A1. Then CV will equal to CV, which is A minus R bar plus BT plus CT square plus D multiplied by TQ. Just go to the integration, and then we can calculate delta U, but per unit mole will equal to integration of CV dt from T1 up to T2. Just to get this equation, depending on the substance, just substitute. Then we can calculate delta U, but I need delta U per kilogram will equal to delta U per kilomole divided by the molecular weight. And this molecular weight can be just given, is given from table A1, depending on the substance. We can get this value. Divide delta U by this value, we can get delta U. But as I said, this case is just maybe for your knowledge, because it's a tough procedure to do the integration and to calculate all of this constants. So in your exam, inshallah, or something, the case is not related to your exam, but this is application also in engineering life. If we do have gas, you can follow either the constant specific heat analysis to calculate delta U or the variable specific heat analysis using the table. Getting back, again, just to remind you, with the first law of thermodynamics for a closed system, Q minus work equal to mass multiplied by U2 minus U1, or equal to mass multiplied by specific internal change of internal energy. We have considered this term heat transfer, we have considered the work, and we have considered other work and boundary work, and also this term how to calculate delta U if the working fluid is either steam or refrigerant, or in case of we do have solid or liquid, and also in case of we do have gas, we do have two special cases, constant specific heat analysis and variable specific heat analysis. And this is the first law of thermodynamics. We do have nothing more in this chapter. This is the case actually, and this is actually all of the equations. These are all of the equations that are considered in chapter 4. So first of all, we have to decide about the system. Either the system is closed system, you have to decide this, the system is closed, and then we can apply the first law of thermodynamics. And then you have to decide about the working fluid so that you can calculate the value of delta U. If we do have gas in a piston cylinder device or something, so in this case we have to decide about the boundary work, which equation will be used to calculate the boundary work. Then we can just apply in this equation. Usually you need to calculate the heat transfer or the work done, and simply we can do it. That's all about this chapter. So thank you.